CH 908, Mass Spectrometry Lecture 7 Tandem Mass Spectrometry. Professor Peter B. O'Connor. Tandem Mass Spectrometry or MS/MS. Isolation. Fragmentation. Isolation. Fragmentation. Benefits. Extremely high specificity. More structural information. Limitations. Isolation window. Fragmentation efficiency. Ion losses. MS/MS/MS, or MS3. MS/MS. Tandem mass spectrometry. Tandem in time, FTICR, kitons. Tandem in space, triple quad, TOF/TOF, sector, outline tandem in space instruments, tandem in time instruments. Sectors. Triple quads. QTOFs, TOF/TOFs, unique instruments, pentaquads. Orbitrap, sort of. Tandem in time instruments. Ion traps. Classic 3D. Linear ion trap. FTICR. MS/MS methods. CAD. ECD, plus ETD, ED, etc. PD, UVPD, EMPD. SID. Magnetic sector instruments. Ions are deflected and accelerated down a curved path to the detector. Magnetic sector mass spectrometry. In summary, by varying the voltage or magnetic field of the magnetic sector analyzer, the individual ion beams are separated spatially and each has a unique radius of curvature according to its mass/charge ratio. High-resolution isolation requires very stable high-voltage power supplies, magnetic field, and very narrow slits, micron. Isolation resolution of 103 to 104 is possible, but it comes at the cost of sensitivity. Usually a mass window of 5 wide is selected. Time of flight mass spectrometry, TOF-MS. Separates ions based on flight time. High-resolution isolation requires very stable high-voltage power supplies for the source, high timing accuracy and rapid response in that is, picoseconds. Usually limited to an isolation resolving power of 102. Usually a mass window of 5 wide is selected. Figure 6. Multi-tandem time of flight mass spectrometer. Laser. Source. Deflector. Collision cell, VC. VR versus. Plus. 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 First field free drift region. Plus. Plus. Versus. Plus. Delay generator. Plus. 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 Second field free drift region. Detector. Oscilloscope. Figure 6. Multi-tandem time of flight mass spectrometer. Aerosol mass spectrometer. Time of flight mass spectrometry, TOF-MS. Separates ions based on flight time. Timed ion selector used for separation. In MALDI, metastable ions have the same flight time as precursor ions, so it is often impossible to completely select the precursor ion. Triple quadrupole. MS3. http://dx.doi.org/10.1016/0168 Watt, MS/MS scan modes. Ions in an oscillating electric field. A plus minus equals U plus minus of sin omega t. Matthew Ekn. As equals 8U slash M omega 2 R2. QZ equals 4 electron volts slash M omega 2 R2. Z stability. R stability. 0.5. 1.0. 1.5. QZ. Operating line. B equals 1.0. QZ equals .908. Stable. Z and R. As 0.2. 0.0. Minus 0.2. Minus 0.4. Minus 0.6. 0.4. Plus. Dash. QZ of VM. QZ of Pheon. As a UM, Z is stable, R stable as QZ. QZ equals 0.908 ABBR and Z stable D. 0.5. 1.0. QZ. As 0.2. 0.0. Minus 0.2. Minus 0.4. Minus 0.6. Z stable. B. A. R and Z. Stable. D. As equals 0.02, QZ equals 0.7. As equals 0.05, QZ equals 0.1. C. C. D. are stable. As equals minus 0.2, QZ equals 0.2. As equals minus 0.04, QZ equals 0.2. Figure 12. Matthew stability diagram with 4 stability points marked. Typical corresponding ion trajectories are shown on the right. Ejection frequency. Items, theory of MS/MS. Isolation waveform is applied to mass select precursor ion. A dipolar resonant excitation amplitude is applied to the end caps. The selected ion gains energy and undergoes collisions with the atoms and dissociates via SID. The fragment ions with stable trajectories are trapped and mass analyzed. QZ isolation equals 0.80. QZ excitation equals 0.25. Scan function for MS/MS on kit. Time. Ion. Injection. Isolation. Excitation. MZ analysis. RF amplitude. Tailored. Waveform. Resonance. Excitation/ejection. Amplitude. Baer, M.E. and Schwartz, J.C. in Electrospray Ionization Mass Spectrometry. 1997 259. Ion trap isolation. Resonant ejection of particular ions, or ranges, is the standard method of isolation. The resonant pulse can be created in many ways. Resonant ejection of one ion usually involves simultaneous ejection of other, lower MZ, ions. Isolation resolution can be as high as 103, but is rarely used above 102, or a 3 to 10 window. Ion recovery efficiency after resolution is the highest possible with mass spectrometry. Excitation/isolation methods in FTICR. Stored waveform inverse Fourier transform. Marshall, A., G., T., C. L. Wang, et al. 1985. Tailored excitation for Fourier transform ion cyclotron resonance mass spectrometry. JMA. Chem. Soc. 107, 7893 to 7897. Correlated harmonic excitation frequency, CHEF. High-resolution ion isolation. Isolation of single isotopes of ubiquitin, 8.6 Ga, and carbonic anhydrase, 29 Ga, was demonstrated. O'Connor, P., B. and F. W. McLafferty, 1995. High-resolution ion isolation with the capacitively coupled open cell, J. Am. Soc. Mass spectrum. 66, 533 to 535. FTICR ion isolation. Resonant ejection of particular ions, or ranges, is the standard method of isolation. The resonant pulse can be created in many ways: sweep, swift, FNF, SHEF, etc. Resonant ejection frequencies are largely independent. Isolation resolution can be as high as 105, but is rarely used above 103-1 the window. Most of these isolation methods result in off-resonant ion excitation, which can lead to fragmentation or poor performance due to magnetron expansion. Fragmentation methods. Breaking up a molecule requires putting energy into its vibrational modes or causing a reaction that breaks a bond. Collisional activation, CAD or SID. Photo-dissociation, ERMPT and UVPD. Surface-induced dissociation, SID. Electron-ion reactions, ECD, ETD, ED, EDD, AIECD. Metastabilatum dissociation, MAD. Collisionally activated dissociation, also called collision induced dissociation, CID. Plus N2. Ions smack into neutral gas molecules and break up. Energy of the collision is controlled by changing the kinetic energy of the ion. Fragments scatter radially. By far the most common MS/MS technique. Slow fragmentation method deposits vibrational energy throughout the molecule prior to fragmentation. SORI CAD, ITMSN, triple quad, TOF/TOF, etc. Figure 14. Quadrupole time of flight hybrid. Oscilloscope. Laser. Delay generator. Source. S. Pusher, VP. Plus. 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 Q0. Q1. Q2. V. RF only. Mass filter. RF only. Plus. 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 Focusing. Collision cell. D. Field 3 drift region. Plus. 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 VRVP. Figure 14. Quadrupole time of flight hybrid, collisional activation in a kit. A plus minus equals U plus minus of sin omega t. Matthew Ekn. As equals ADU slash M omega 2 R2. QZ equals 4 electron volts slash M omega 2 R2. Z stability. R stability. 0.5. 1.0. 1.5. QZ. Operating line. B equals 1.0. QZ equals .908. Stable. Z and R. As 0.2. 0.0. Minus 0.2. minus 0.4, minus 0.6, 0.4, plus, dash, QZ of EM, QZ of Pheon, as a UM. Collisional activation inside FTICR. Gautier, J. W. T. R. Troutman, et al. 1991. Sustained off-resonance irradiation for CAD involving FTMS. CAD technique that emulates infrared multiphoton dissociation. Anal. Kim. Acta 246, 211 to 225. Mirgorodskaya, E. P. B. O'Connor, et al. 2002. A general method for pre-calculation of parameters for sustained off-resonance irradiation/collision induced dissociation. Journal of the American Society for Mass Spectrometry 13, 318 to 324. Photo-dissociation H-epsilon ion absorbs photons and break. H-epsilon ion absorbs photons and break. Energy of the fragmentation is controlled by changing the photon's wavelength. No scattering, except for multiply charged ions. Slow fragmentation method deposits vibrational energy throughout the molecule prior to fragmentation, depends on wavelength. EMPT, UVPD, BIRD, UV photo-dissociation. High energy environment, cleaves the backbone yielding A and X radical cationic species which further dissociate. If too much energy or wrong wavelength, 193 nanometers, only ammonium ions are observed. 157 nanometers photodissociation. EMPT ions are heated using a CO2 laser until they dissociate. Fragments follow lowest energy pathways, which means preferential cleavages. Fragments remain in the laser beam and continue to absorb, resulting in secondary fragments. Infrared multiphoton dissociation. Surface-induced dissociation. Plus. Ion smack into a surface, break, and rebound. Energy of the fragmentation is controlled by changing the ion kinetic energy. Fragments scatter radially. Slow fragmentation method deposits vibrational energy throughout the molecule prior to fragmentation. Ions are lost by neutralization at the surface, much better with perfluorinated surfaces. Sidin and FTICR. Surface-induced dissociation. Electron capture dissociation. M+, N+, N1+, E. Multiply charged ions capture a slow electron. Energy of the fragmentation is determined by Coulombic recombination. No scattering, but if both fragments are charged, Coulombic repulsion will occur. Fast fragmentation method involving a radical rearrangement in the region of the backbone carbonyl, for proteins. Generates very predictable and very even sequence ladder. Nobody knows how it works on things other than proteins. Odd versus even electron fragmentation. Even electron equals proton rearrangements. Odd electron equals radical rearrangements. Non-ergodic fragmentation equals fast. ECD spectrum. Substance PECQFFGLMNH2C5C10C7C4C8C9A7Z9W2300 M+2 H+, C6, C4, C8, C9, I7, Z9, W2, 300. 600, 900, 1200, 1400, 400, 500, 700, 800, 1000, 1100, 1300, MZ. RPKPQFFGLM 674.8 equals M plus 2H2 plus 1348.7 equals M plus 2H plus Z9 slash Z9 C7 slash C7 C9 C10. Self-assessment. How do you isolate ions in a TOF instrument? An ion trap? An FTICR? Isolation and fragmentation of ions in an ion trap, using CAD, results in losses of ions below 30% of the precursor mass. Why? For proteins/peptides, CAD results in what two main fragment types? For proteins/peptides, ECD results in what two main fragment types? CH 908, Mass Spectrometry. Lecture 1. Feeney. Magnetic sector mass spectrometry. Magnetic sector mass spectrometry. Theory. The ion source accelerates ions to a kinetic energy given by K equals half mv2 equals qv, where m is the mass of the ion, v is its velocity, q is the charge on the ion, and v is the applied voltage of the ion optics. Magnetic sector mass spectrometry. The ions enter the flight tube and are deflected by the magnetic field, B. Only ions of mass-to-charge ratio that have equal centripetal and centrifugal forces pass through the flight tube. mv2/r equals bqv, where r is the radius of curvature. Magnetic sector mass spectrometry. mv2/r equals bqv. By rearranging the equation and eliminating the velocity term using the previous equations, r equals mv/qb equals 1/b2v m/q half. Therefore, mq equals b2 r2/2 volts. This equation shows that the mq ratio of the ions that reach the detector can be varied by changing either the magnetic field, B, or the applied voltage of the ion optics, V. Time of flight mass spectrometry, TOF-MS. Theory. K equals qv when electrons are accelerated through an electric field. K of ion is half mv2, so qv equals half mv2 and velocity is inversely proportional to mass. Transit time, t, is Lv, where L is drift tube length and v is velocity. So T equals L/2 volts/m/q half can be solved for charge mass ratio. Time of flight mass spectrometry, TOF-MS. How ITS done? Reflectron is series of rings or grids that serves to focus ions to improve resolution. Exact values of L and V do not need to be known if two or more ions of known mass are used as mass calibration points. Produces a mass spectrum as a function of time, can be measured every 10 sec. Time of flight mass spectrometry, TOF-MS. Advantages. Good for kinetic studies of fast reactions and for use with gas chromatography to analyze peaks from chromatograph. Can register molecular ions that decompose in the flight tube.